Take two. Now you are.
Hello everyone, my name is Waseem. I'm an AI researcher at 20 billion Neurons, and we work on deploying deep learning models on video. So today I'll be talking about a paper, Show, Attend, and Tell, Neural Image Caption Generation with Visual Attention. It comes from a variety of collaborators. So let's get started. So the general overview of the paper is they perform image captioning using high-level VGG19 features. There are two types of attention mechanisms that are proposed, soft attention and hard attention. And most of the focus in this paper is on the decoder side. So if we look at the architecture, we have an input image that is fed into VGG19 CNN, and it's image not pre-trained, so we extract the 14 by 14 feature map. This feature map is then fed into an RNN, which computes the attention values over the image, which then is used to output the words one by one. Simple enough. This part is more or less straightforward, so we will be diving in the second part of the architecture. So the first attention mechanism proposed is the soft attention. It's deterministic. It's based on Badenow's attention mechanism from machine translation, and it's trained using backpropagation. So how does it look like? We have an image that is passed to a CNN. As I mentioned, it's a VGG19 image that's pre-trained CNN, and so we obtain this grid of features. 14 by 14. We also have an input from an RNN that outputs a distribution over the grid locations. So for every cell, for every element in the grid, we have a corresponding probability distribution. And then we multiply these element-wise in order to get context vector. So to get a little bit more into the details, we compute the score of every grid location using a neural network that takes in the 14 by 14 feature map and the previous LSTM hidden state. In order to make it a probability distribution, we apply a softmax operation. Then we perform an element-wise operation between the distribution and the feature map values, and we multiply this by some gating parameter beta, which is extracted using another neural network using the previous time step and passed through a sigmoid activation. This makes sure that the value of beta is between 0 and 1. If the value of beta is closer to 1, it focuses more on language modeling. It focuses more on the LSTM features. If the value of beta is closer to 0, it focuses more on what's in the image. Anyone has any questions?
Just clarification, G sub
It's the 14 by 14 feature map.
Okay.
So because it's called grid there, I just added a bit G sub I. Yeah.
The sequence matters, or how do you define the sequence of the input to the RNN?
Oh, so for it, the input to the RNN is the image. So we're using the RNN in order to we're using the RNN along with whatever is extracted from the CNN to give us scores, and then these scores are normalized to probabilities, which are then multiplied to give the context to give a context vector. And the idea is that regions that have higher probabilities, the network focuses more on grids that have higher probabilities.
The question is in the CNN, like in the 14 feature, you have like 128 feature maps. How do you?
196. It's 14 by 14 by 512.
Okay, 5 feature maps. How do you put that translate to an input to this RNN? It's like a.
You don't input it. It's not quite input to the RNN. It's input to the neural network that computes the score for every grid location. We have a neural network that takes in these features and takes in the previous hidden state of the LSTM and outputs a score here, a score here, a score here, a score here. So it outputs a 14 by 14 by 512 score. And then we perform a softmax operation in order to make it a probability distribution. Okay.
So kind of related to that, so what is H then? That's the hidden state of the RNN?
Yes.
So what is the probability of? You're saying the probability each of these grid locations has a probability?
Yeah, they are produced using the feed-forward neural network, FATT.
But what is it a probability of? Like what does it represent?
Oh, okay. If you look at the denominator, we're looking over the entire feature map. Okay, so it's getting normalized across the entire feature map. It tells us basically which grid locations the model should be focusing more on. You know, so for example, if this probability is high and this probability and the rest of the probabilities naturally become low, and so the context vector will mostly contain these features because
So it's kind of like importance.
Yeah, but it's called attention.
I have a question that's sort of follow up on the RNN. You said it doesn't feed in the features into the RNN, right?
Yes.
So what feeds into the RNN?
The previous token. So the RNN basically takes in the embedding, and then that updates its state, and then using that value we compute all of these. Right? We have to output a caption in the end, and so this every token that's output at every time step gets fed back.
So do you mean the RNN just the decoders, not?
Yes, more or less. It helps. It is in the decoding process because then we take the context vector, we take the embedding of the previous token and the hidden state of the previous time step as input to another neural network that gives you the output probability of the next token of y sub t.
Very quick question. How do you tell? You did mention the intuition where if data is closer to 0, then it's more generative, and like with the RNN side?
If it's closer to 1, it focuses more on the LSTM. If it's closer to 0, it focuses more on the image.
How is that?
Yeah, they mentioned that in the paper as an intuition for why beta could be a gating parameter.
If you have an equation where you have like a summation of the two different parameters, then I would see that happening. But this seems to be just experimental.
And in this particular case, it can simply be the other way around, right? If beta was small, then then you can also focus on the context. But if I had to guess, it would probably be something to do with the scores here, probably. If I multiply h sub t minus 1, if I feed a neural network and z sub t is small, then it's gonna if beta is small, z sub t is small. So the features that it gets are gonna be of higher value from the embedding and the previous hidden state. But if beta is closer to 1, then this gets more emphasized.
Otherwise, it's basically. But ZT is technically also the embeddings from the hidden state from the previous time step, right?
No, it not quite.
Oh, it's just it uses beta as the attention.
Yes, as a gate
strength.
Yeah. So if beta was small, you would expect this to be small, so it wouldn't have much effect on the output. But if z sub t was high, you would expect it to have an effect.
Makes sense.
And so the authors also employed something they call doubly stochastic attention, where they want to encourage the model to look at various parts of the image. And so they add this L2 type of regularization, where if you look at this term, we are summing over a single grid. We're summing over all time steps of a single grid location, and so we want the probabilities of the elements at a single grid location to be equal to 1 across time. So the idea is that this should encourage the model to put some equal probability weight across the entire grid. I hope it's clear.
What's L?
L?
Yeah, 1 over L. I mean I from L.
This one?
Yeah.
Oh, this is the number of grid locations. So it would be 196. So 14 by 14.
Oh, okay.
It's in the paper. I didn't put it in.
Yeah.
Could you state the intuition once more?
So this is this is the attention probability on a single grid location, right? And so by summing over all time steps, okay, we want to make the probability over a single grid location. So if I go back here, to be roughly equal to 1 across all time steps. So if let's say I unroll this across time, I want the sum of P sub A across the first time step, second time step, third time step, so on and so forth to be equal to 1. The same goes for P sub B, P sub C, and P sub D. And the intuition behind that is you kind of encourage the model to look at different parts of the image instead of sticking to like the middle of the image or to the side of the image.
What do you mean when? Maybe I know you're using RNN, but I'm just confused. What do you mean when you're saying time steps? Because this is an image; it's not a video, right? So
Yeah, but you're outputting captions.
sorry.
The task is you get a caption, you get an image as an input, and you output a caption, which is a sentence, right? And the RNN outputs one word at a time. Okay, so if
That makes a lot of sense.
I have a bird flying over a body of water, and so this is the first time step, second time step, third time step.
Thank you.
Yeah.
So that second term was a cost if you go to the was a cost if it's only paying attention, but well, if one of the grid locations is receiving a lot of
Attention. Yes.
So that's a cost. Therefore,
Yes.
you want it to move around.
Yes. You want. It's more about allocating probabilities in different places.
Kind of okay. That was comparative. I shut myself down. Please go ahead.
Okay. All good for now? Because I think we're pretty much done with this part. Yeah.
Self-attention.
Yeah.
How do you force the TA in that direction sum to 1? It's like maybe one layer the TA not be very big, right?
Yeah. You're not forcing it. You're just again. It depends on the value of lambda. The higher the value of lambda, the stronger the stronger the effect on the model is going to be. The smaller the lambda, the smaller the effect on the model is going to be. This is just something you want to alter the model's tendency. You want it to be more likely to look around the image than not. That's the whole idea behind this. It's just like L2 regularization, right? You want the values to be small, okay? And depends on how much you set the regularization factor. The higher it is, the smaller they're going to be. So basically, the learning process trees off these two factors.
Why don't they take the average of the probability? Because all the probability.
Could you please speak up so that the camera can pick you up?
Why don't they take the average? You sum all the C, right? Like 1 to C times stem of the probability. So why don't they take the average of that? Because all the grids probability add up to 1, right? The probability
Yes.
of the grids. So this is going to be very likely greater than 1 because it's C times that, right?
It depends. So I mean overall, if you square it, I think it will most likely be less than 1 because most of the probabilities are going to be small. So 1 minus a small probability is going to be less than 1. Square is even less than 1.
Okay.
But I think because the probability just gets normalized to be between 0 and 1. That's why they've used that.
So there's our one. Because when you go back to the last slides, I assume those P is PA, let's say PA, for 10 times, like C times. Is that what you mean?
I'm sorry, P?
Like PTI for T equals to 1 to C, right? If I'm looking at A, like...
Just a minute. T1 to C, that's across time steps. It's across time.
So
this is space.
This is updated every time step or just the whole C? Only update once every C time steps?
I don't quite
It is
follow.
updated every time step, right? So P's are updated every time step.
Yes, the
Okay.
probabilities are
And
updated
then-
every time step.
Okay, can you go to the next one?
I think if I show you this example, you will get a better idea. So what we have is an image, and we have the model starting to predict a. It produces this is the value of beta. That's the first thing that springs to my memory. 0.97. You can see stop. There is still high attention on the stop sign. Okay, and you can see that the value is dropping, which means it's trying to get that information from the image more than the language modeling part. Yeah, the authors do say that introducing this beta variable makes their model tend to look more at the image. We should also be a little bit cautious with saying that if beta is greater than 0.5, then it's more likely to be language modeling. I think the threshold is kind of arbitrary. So we have is on until it comes here on and finally road. It actually kind of starts looking at the road down there with a mountain, looks around the mountains in the background. Actually, it starts to look at the background and then it generates the full stop. So yeah, so this scheme makes the whole model seem more interpretable. You understand sort of why the model does what it does.
What's the number in the bracket?
Beta, I think.
You said
That's the first thing that comes to my head. Yeah.
You said higher values are biased more towards the language model?
Yes. So it predicts a because I guess most captions start with a.
What about the last one? Wouldn't you expect the last one to be more based on the current state of the sentence?
It depends. Again, that's why I'm saying we shouldn't be too strict that since, for example, let's say is on, this is 0.25, doesn't necessarily mean that it's focusing more on the image than the language model, because you don't really know what the baseline is, sort of. You don't know what the you don't know where to set what's high and what's low. It's learned. Yeah.
Is there a predefined limit for the unrolling steps for the RNN?
Typically, yes. In practice, you do have a maximum number of time steps that you can unroll the RNN to, and you usually have an int or like blank token. So that's why it's not there. We can talk about the details of that after the talk. It will be mentioned. Yeah.
So you're saying a higher beta is closer to a language model.
Yes.
So if it didn't have the image, I would have thought that like a stop sign is on the road, so I would have expected the beta for the road to be higher, just based on language, forgetting about the image.
Yeah, but that's why I'm saying that setting what's high and what's low for beta at every time step is going to be tricky, because it's just a parameter that's learned, and it's a result of the interaction of the embedding of the previous time step and the previous hidden
So
state.
we can't even compare across time steps, these beta values?
I mean maybe across similar time steps, maybe yes, but that's just my intuition talking. So I would say like probably maybe mountain is more likely to be, so for example here in is probably more likely to be based on the image. For example, this dot 0.13 is higher than 0.11, so it's more likely to be language model. But it's difficult to speculate without actually like training the model and actually looking at it.
I want to be argumentative about this, but we can come back to it.
So this is an example where the model gets it right. Let's look at an example where the model gets it wrong. Again, it starts with an up, and then it says man wearing a hat and a hat on a skateboard.
Yes.
So you can see when it says man, it focuses sort of on the face. Again, you shouldn't read too much into this. Okay, like just because it's saying hat and the model is focusing at the top of the image doesn't really mean that the model knows that hats are on the top of the are at the top of the head, come to the top of the head. It could just be a statistical thing. Yeah, and you can see, for example, when it comes to skateboard, it kind of focuses more on the violin. For some reason, it thinks it's a skateboard.
But you could say the same about the dot. It focuses on the violin as well.
Yeah, but okay, but don't forget there is a beta value, and this beta value.
Not that far from the point 15 that you have.
Yes, true. But I'm just saying. But yeah, but I'm just saying that again, we cannot say what's a good, what's too high for a beta, what's too low for a beta. It's something that the model sort of knows.
I can see two hats here.
You can or can't?
I can.
Okay.
And actually the difference between the scores is
Yeah, but it's the betas. It's not a score. It's a gating parameter. So yeah, it's not a probability as far as I remember.
Did it have violin in its training data? As a generation? Probably not, right? Because it would.
I hope so.
You would at least you would. It would be more likely to output like a UNC symbol, like unknown, instead of skateboard. But yeah, it could also be. I mean, my intuition would say that it sees something wooden somewhere at the bottom of the image, therefore it's a skateboard. Yeah,
it's true.
Yeah. I mean, just like cars, you know, there is something that's going on the street with trees. It's a car. Yeah. So it's. Yeah. These models would do whatever they can to cheat. Like, yeah. So I experienced it. Okay. So yeah.
Does the paper tell you if there's a way to know if the embedding is messing up or the language model is messing up in that case?
It's actually one of the shortcomings of this paper. There is a lack of ablation studies, but the paper already how to say it? It already provides a lot of content that there's pretty much no space for this type of analysis. Right? On to hard attention. So unlike soft attention, this is actually stochastic, and works by assigning a multinomial distribution to the attention weights P that we saw, and view the weighted input Z as a random variable. So this is the context vector. We estimate the gradient using Monte Carlo and train it using the reinforced learning group. So let's look into that, implementing hard attention. So again, we would like to maximize log probability of the captions given the feature maps. Okay, whatever feature map that we have at this point, we want to maximize the probability of the correct caption. And so one way we can write that down is by expanding this probability term into these two terms, where the probability of S, a variable, time t, location I. So basically S is just location variable. So t is the time step and I is the grid location. Okay, and if its probability is equal to 1, then well, the probability of this variable being equal to 1 is basically equal to the attention weight that the model learns, right? So if we think about it, this is stochastic, so we either pick it or not, okay? And so the expected value of picking a value at a specific grid position at a specific time step is going to be equal to its expected value, which is actually the one that's output by the soft attention. Okay? And so we have this inequality that says that the log of the expectation is greater than or equal to the expectation of the log. And so basically this is a lower bound, and so we would like to maximize this. And therefore, if we maximize this expression, that automatically maximizes that expression. And to calculate the loss, just take the derivative with respect to the weights. We use the product rule, so we take the derivative of P of S given G with respect to the weights, and the same thing here. And so now we would like to convert this gradient into a form that is computable, that we can actually calculate or roughly estimate. So this is the expression that we have. And so one thing that they use is this is reinforce, which basically uses the fact that the derivative of the log of a variable is equal to 1 over the variable times the derivative of that variable with respect to the original variable. And so we can rearrange this expression to look like this. So basically we just multiply both sides by probability of S given G, and we get this form. This would allow us to replace this term with this value, and we'll see. You'll see what's the point of that. So basically, the good thing about this is now we have probability of S given G here for this term. We have probability of S given G for this term. So we take both of them out. All of a sudden, you can see that we can actually convert this to an expectation, and therefore we can approximate it via sampling. Therefore, we can sample different locations. Well, they assume that they're going to sample it using multinullity, they assume a multinullity distribution over the attention weights. And so once you have a sampled location, basically you plug it into this estimator, and you basically sample and you average those. And that gives you a rough estimate of the gradient. Yeah.
What's the W here? I'm assuming these are
the weight
weights
parameters.
For what?
The neural network weight parameters.
Okay.
Yeah, so you want to, because you want to maximize that expression, you want the gradient to move in such a way, of the weights in such a way to maximize L sub S.
I didn't understand the last step in the previous slide.
This one?
So, okay, so you're doing a bunch of math, but then you said at the end you're trying to get to that format because you can approximate that with sampling?
Yes.
Okay, can you explain that?
So so the probability of sampling a grid location given the grid parameters is actually calculated by the soft attention weights. Right? We can see that by having these soft attention weights across the grid location, we can see that applying a multinullity sampling scheme to that produces a stochastic sampling, which is pretty much hard attention, which is pretty much exactly hard attention, which is what you want. So okay, let me rephrase that. You should probably edit that. Okay. So we have the probabilities which are output by the attention portion, and then we sample it using a multinullity sampling scheme, so we get some grid location, right? Once we get that, that's already one sample. Keep in mind that P sub I depends also on the grid location, so we can see it as an instance of the grid location given the feature map. I don't know if I was clear about that. Somehow. If anyone has any questions, please feel free.
So this is just finding the expected value, and because this expected value, you can just do sampling.
One way to approximate the expected value is to do sampling. Yes, but he was arguing why this part, like why can this be sampled that way? I think.
Oh, I see.
Yeah. All good? Yeah, so this gives you sort of an estimation for the gradient. You think it's done, huh? It's not done. So the issue in this gradient calculation is that its variance is too high. So this is an issue that you constantly bump into when you're doing reinforcement learning as well. The value of the gradient fluctuates a lot, and that makes updating the parameters sort of inefficient and very annoying. So in order to counteract that issue, we take some sort of a bias value from the previous mini batch, multiply that by 0.9, and then we add the log probability of the caption given the sampled grid location and the feature map. Yeah, we take this probability multiplied by 0.1. So we take the output of the output generated by the neural network, log that, multiply by 0.1 to get the new bias. And why do we need that bias? So we need that to subtract in order to make the variance of this expression smaller. So this is actually one of the hacks that are employed in order to reduce the variance in the estimation of this gradient. They also add this lambda sub r factor in order to control which part of the gradient should contribute more. What you need to know is that these are just a bunch of things that are being used to make training this model possible. Any questions? Yeah.
So why in this case is what's being output by the LSTM, or are we using a completely different model here? Like what is y? Where is y coming from? Y is the label, or is that?
It's the caption.
Is the caption?
Yes.
So yes, coming out of
yes,
it's coming
it
out of
is.
the LSTM for that timestamp. For that timestamp.
Yes.
Okay, that's. I just wanted to double check that.
Yeah.
My
in this particular case, it's probably the sum over all time steps, because there is no sub-T here. The authors don't. The authors talk about this on the mini batch level. So this is probably the output over all time steps, and instead of because you have the log, you can sum the log of the probabilities.
Right.
Don't you have many words though?
Yeah.
So
You
how
just
do
you'll have to sum them.
I don't understand.
some words?
Sum the probabilities
Okay,
of the
that
words.
makes more sense.
Oh, the log probabilities of the words.
I don't understand why when you have the bias, when you change the bias, it reduces the variance.
Oh, it basically gives you an.
So the question was why inputting bias would reduce variance. That was
Yeah.
the question. Please.
Yeah. Okay. So the whole idea is that let's look, for example, at the log. Okay. If we take the log of a value, it's a log of a probability. It's going to be somewhere between -infinity and 0. And so if you just subtract the value, you are already moving the you're already reducing some chunk of the variance. Remember, this value is negative, too, and so you're just the whole idea behind this is that you only want to know the direction of the gradient. You don't really want to know the exact value of the gradient. So that's the thing.
Is this reduce again something between kind of max 1, right? Because you have like 0.9 and 0.1.
This is geometric weighted. It's trying to put more emphasis on the previous mini batch, on the biases of the previous mini batch, than on the probabilities that are output by the model.
It's basically smoothing it. Is really all that matters, right?
This part is you can say that this part is smoothing in order to make this expression more.
Can I think of it like as a momentum on that term? It is comparative, I know.
On some level, I mean, yeah, because I mean, if you replace B with the original expression,
then it is momentum term.
It is like it's like subtracting this portion, and this is as if you're introducing some sort of a geometric momentum. Yeah, it's momentum. Yeah, I guess that's a good way of looking at it. But yeah, you run into these issues in practice with reinforcement learning all the time, and so people actually put these biases in there. There are very different. There are a lot of different ways in which this can be implemented. Okay.
Question.
Yeah.
Why the variance is so high? Because you only penalize first part, second part.
Because you're taking derivative of the log of a probability with respect to the weights. So probability is between 0 and 1, log is between minus infinity and 0, and the derivative of that with respect to the weight can be huge.
But the second part, like the last equation, the second part you didn't use a moving average. The second, the last equation, that one. Because you only use a lambda to multiply the first gradient, the second gradient, didn't you?
Yeah, actually it's one of the things that I'm criticizing the paper for as well. But I checked the code, but I don't remember what the value of lambda sub r is. My guess is because you had to multiply this by the log probability, might have influenced it more or less. We'll have to look at the source code to figure out what lambda sub r was, and if that value was really high, that means they were trying to make this overshadow this portion. Yeah, it's also one of the things I was thinking about actually. Yes. So, oh yeah, there is further variance reduction actually. Okay, just when you thought it's done, right? By adding entropy term to the tension weights. So basically, you have another factor where you have the entropy across the grid location, but thankfully this is just simply the attention values, the values output by the soft attention. Yeah, so it's something more manageable. But again, with 0.5 probability during training, S, the sampled grid location is set to its soft attention value. So as you can see, this thing is very, very, very difficult to train. Has probably been, probably has had a very high variance, and they probably had to implement a lot of these tricks, so to speak, in order to actually make this thing converge. Okay, so they do end up using part of the soft attention in order to estimate the hard attention policies, so to speak. And so, just to look at some at the positive example, we have it doesn't even look at the giraffe standing. So yeah, so there is no beta here, so that's why there are no values. Looks at the corner it's just looking at the corner field with, then finally it kind of probably looks at the giraffe. One thing you need to note is that just because it's not looking at the giraffe doesn't mean it doesn't see it. These are 14 by 14 feature maps, and VGG19, if you look at the 14 by 14 feature maps, actually has a very large receptive field. So if it looks at the grid location here, it probably sees the entire image. I'm almost sure it does. Yeah.
So what are you showing? Is just only the hard attention?
Yes. Yeah. And so, at the same time, for example, a negative example is a dog. So, yeah. Here, actually, no, that I remember the authors just so because the because the feature map is 14 by 14, and the original image was 224 by 224. I think the upsample the grid location, like just to make it visible, the upsample it 32 times in order to make it sort of more comparable with the original input. So yeah, it could, as you can see, because of that, it doesn't really have to look at the object in the image in order to output the caption itself. It just needs, basically it just needs to figure out which part of the image should be assigned hard attention. Any questions about this?
Do they cite anything from these positive and negative examples?
I'm sorry?
Do they make any conclusions from these two samples based on where the attention is strongest?
They actually explicitly warn that just because they have this part highlighted doesn't mean that the network is only seeing this part of the image. It just happened to be the part that is sampled from the multi-nully sampling procedure. Whether they conclude anything, I think from soft attention they just state that the model is kind of more interpretable. But in my opinion, the same thing is happening with soft attention too. If it focuses on any grid location, that grid location already contains information from multiple features from a huge already has a huge receptive field, and so it contains a lot information from a large part of the image. Same thing, they mentioned that consecutive grids, the grid cells have actually high overlap, so they actually overlap a lot together. Yeah.
I mean, it basically means that the position is very, very rough.
Yes, and it's not indicative of. Just because it's there, it doesn't mean that's what it looks like.
So is that why they show? I'm wondering why they put these images in the paper. Is it to show that where the attention is doesn't actually necessarily correspond with?
There is an argument that it roughly corresponds to like the area around it. Okay, but again, that largely depends on which features the network obtained from the layers below.
Because even in the previous example, field was in the top corner, totally separate from.
Yeah. But still, I mean, okay. So there is actually two interpretations here. Looking, it looks down for trees, it looks up for field. Yeah, it's a little weird, but it probably just sees that it's green, so it's probably field. At the same time, here it sees that it's green down there, so there are probably trees. But again, it largely depends on what information was propagated from the earlier convolutional layer.
Beauty of a huge network.
You mentioned that, so the sections are the 14 by 14, and how did they get that from there to the original image?
Yeah, so the upscale. So for example, let's say that the grid location was here. They mark the pixels around it. I think it's 2 to the power of 5. They mention it in the image. They basically have some sort of Gaussian smoothing or something. It's in the final paragraphs of the paper. They mentioned that.
So regarding that regularization you talked about earlier, that wanted to bias the network to look at different parts of the image. It looks like here the top left corner is actually quite popular spot. So
yeah, because that's also where hats are, right? So that's true, and that's completely like valid point. This does show that there is some bias in the model towards looking in that direction.
But
at the same time,
at
the same time, you should keep in mind that the model can sometimes just decide to look at the language model and output the entire caption. So one thing is that for example, that I noticed at my work is that let's say you cut off the image here and you just let the language model run, it would probably output all of this just from the language model based on the training data.
So could it be grammatically is getting it right, although it may be spotting them wrong, but grammatically it's just getting it right? Because what you're saying, if you do what you just said, if you get rid of the image, it probably still will come up with this because of the training it got.
Yeah.
So what I'm saying is, even if it gets it wrong, that identification of things, because of the grammar, it kind of gets it right.
I mean, again, so
how much
it
cache?
it relates to the LSTM dynamics. So when you let it just run, okay, the LSTM just chooses a manifold to generate on.
Do they show a comparison with, say, 3 samples, one where there's only image, one where there's only text?
It just said, yeah, ablation studies is one of the limitations of this paper, but there is another paper that shows that these models cheat in that way. That if you just if you don't provide the image, it basically just generates the entire caption just like that.
And
even
how
without.
close are they when they? Well, it's a different paper, so.
Yeah.
Could it be that the top left corner corresponds to index value 0?
The top left corner corresponds to what?
Index value 0. So it's like nothing.
Yeah, it probably is grid location 0, but I think it's just indicates where the model is probably looking in the language model. Again, it's difficult for me to say, but it's just from my intuition and the work that I've been doing with these models, I can say that.
It's like a beta zero?
Yep.
So two clarification
So the beta
questions.
is 0.
Two clarification questions. So one, does it have? Is the LSTM is this pre-trained? Do they use pre-trained embeddings, or it's just?
The embeddings were pre-trained, I think. CNN ImageNet pre-trained. The LSTMs.
They're not pre-trained.
No.
But did you say the embeddings are?
Yes,
pre-built
I
embeddings.
think so. I think they were.
Okay. Also, so I remember the part where we talked about the feature map, and the feature maps should sort of involve a lot of the pixels, not just one. So I was wondering, how does it exactly pick that tiny pixel on the image?
It largely depends on the features that were propagated. So from the image up to the 14 by 14 feature map, right? So different grid locations would probably
so
capture.
the first layer. So then, because so the feature map basically has a receptive field, a large receptive field
Yes.
over the original image.
Yes. But
the
they
only
could be
way-
capturing different things too, right?
Yeah.
So you could be capturing, so for example, you could be more likely to capture the giraffe's head in the middle, and more likely to capture the trees if you're up, and more likely to capture the field if you're at the bottom. But it's.
I guess what I'm not connecting with is what's the that attention that you're showing the results of? What is it exactly running? Is it on the feature map that we saw earlier, or?
They map the sampled grid location onto the original image by applying what I think is a Gaussian filter with basically they increase the size to accommodate for the increase in the. So the feature map is 14 by 14. The image is 224 by 224. So they increase the size of the Gaussian kernel in order to accommodate for that.
Okay, so the op sample, so the grid is actually much bigger. So it has a lot of more cells to it when they run the attention.
No. The way I would look at it is, if you align these, you would probably kind of get 14 by 14 of these in this image.
I see. So it's still 14 by 14. It's just stretched.
But it's just mapped from the 14 by 14 to the original image, So you have to upscale it. Yeah.
Is the attention there?
Can you speak up?
Is the attention there? That's the output of the RNN probabilities. The probabilities for each grid, right? So you're looking. That's like the highest one.
So it depends. It's actually at inference time. At inference time, I would say it is the maximum one. Yeah, I think at inference time it would be the maximum one, but I don't remember that detail from the paper. But if I had to do it, that's probably how I would do it. Yeah.
So the role of reinforcement learning here is to make the model pick the points on the grid on the image itself. So this is the role to sort of focus the attention to move it around. Is that the case?
Yes, and because that's stochastic, you either choose it or not. There is no smooth value. Like you can't compute a gradient out of that. So you somehow need to come up with a way to compute a gradient. That's what reinforcement learning. That's where reinforcement learning came into play. You can calculate the gradient on these stochastic values.
So there's some probability with which you want to sample each grid location, right? And
Yeah.
use reinforcement learning to sort of approximate that function somehow, right?
You're using reinforcement learning to approximate the gradient, the sampling you just sampled, right? But in order to calculate the gradient itself, you need to somehow get rid of the discontinuity, right? You cannot calculate the gradient on this grid location. You have to come up with some trick to approximate it. That's why all of this was done. Yeah.
Can you go back to the giraffe one? So you said, or this is labeled positive. How strict is it for positive? So for example, if it says,
Oh, this is correct.
Yeah, but if it says a giraffe standing with trees in a field, but the order's messed up, would that still count as positive?
I think it would largely depend on the metric that the authors employed. So the metric is not like a one-to-one matching. There is like blue and meteor, which we'll get to in a bit. These are the metrics used by the authors, and so if the model sort of gets 100% on those, that's definitely a positive. I believe they put like the true positive, like the ones that are 100% positive here, and the ones that are completely wrong here. There are a few examples in the paper. As far as I can remember, they don't have a strict criterion on what's positive or what's negative.
Okay, let's move on. We can come back to it after.
Okay. So as mentioned, VGG19 pre-trained on ImageNet was used as the encoder. 14 by 14 by 512 feature map from the 5th conv layer was used, and the models were evaluated on Flickr30k, Flickr30k, and COCO. Yeah, so in order to evaluate the performance of the model, there were two widely used metrics back then, Blue and Meteor. And so there are multiple versions of Blue that take into account different words. So for example, this one calculates based on a unigram, this is bigram, trigram, quadgram. Okay, and so as you can see, when it comes to Flickr30k, soft attention and hard attention overall perform better than plot by linear model and the Google Neural Image Caption. With hard attention performing kind of better actually here. For Flickr30k, it's the same thing. You can see that the new model outperforms the previous models, and hard attention in general has a higher blue value than the soft one. Here, soft attention has slightly higher value, higher meteor value. And for MS COCO, it's pretty much the same thing. Hard attention has really good blue value, but soft attention has a good meteor value. So it largely depends on your taste. Yeah.
Smaller differences with log to log bilinear though in the last case.
Yeah. So the difference as the blue score increases, a difference between a 1 point difference kind of matters, but not really. So let me explain that. Basically, as the blue score increases, okay, the correlation between blue score and human judgment becomes smaller. But at the same time, a single point increase in blue score is actually something significant. For example, in machine transition papers, if you get a 1 blue score increase, it's like, yeah, that's it. Like you basically established a new state of the art. No one's gonna question it. So yeah, but again, you have to keep in mind the higher this value also. When it's low, up to a certain point, it correlates well with human judgment, but then it starts to degrade. Meteor was introduced to offset that, so Meteor is sort of better in that aspect, but it also has its issues as well.
Can you explain the Meteor metric? Or how it's
Okay, so Meteor uses a synonym. It basically takes into account what blue is doing, and it uses WordNet. It uses the WordNet tree. Yeah, they have a semantic tree where they say, like, for example, mammals and are part of like the animal kingdom, and, like, you know, under mammals you have cats, dogs, humans, and all of that. So yeah, using that semantic tree, they have some sort of internal magic in which they calculate the further the distance, for example, the smaller the factor, the smaller the similarity is, but it's still relevant and stuff like that. So it uses WordNet in order to finally measure.
Pretty limited though. Like not everything is in, and it's very manual. So what happens in cases where they don't have like the entity isn't just in WordNet?
That's why they created more metrics after 2015. Keep in mind that in 2015 was like the start of where all of these tasks were getting rejuvenated, and we were starting to get really large data sets in these problems, and so new metrics were developed. But Meteor still remains actually quite solid till now. I was working with these metrics, and Meteor still quite solid actually. Yeah. So to conclude, in general, it seems like hard attention seems to outperform soft attention. I mean, we saw from the results when we look at blue score, there is quite a bit of difference. But when it comes to Meteor, I mean, the difference here is small. The difference here is okay, but still, like, overall, you can say that. I mean, I would argue that hard attention seems to outperform soft attention in general. At the same time, it's not clear whether the improvement was driven due to a better encoder or not. Compared to these models, these guys used pretty much state-of-the-art encoder at the time, the VGG19. And so it's not clear whether this improvement in scores was actually caused by just a better feature encoder, or because of this hard attention mechanism or soft attention mechanism, right? And that leads me to the third point, which you guys have noticed, which is a lack of ablation studies, right? There is there is no study of how the model performs when there is no attention. There is no study of how the model performs with, let's say, weaker encoders. So I think that there could have been some stuff to be explored there, but I still think that in general this approach was interesting. Thank you.
All right, we're going to take 2 minutes break and then